if you remember from Calculus 2, when we learned the arc length, the arc length is a value. I mean, if you have a specific endpoint, the curve starts at a certain value of t and goes all the way to another value of t, then you have a certain value. But what happens if you don't want to specify the endpoints? You want to come up with a generic expression for the arc length. Then essentially what you're saying is, let's create an arc length function for a general solution. And then once we have that, we can replace the variable, or in this case the parameter t, with the endpoints. So let's look at the arc length function. So we're going to define, here's the s that I was, that's why I didn't want to use s in the previous example. Let's s of t be the arc length function of a space curve C, such that one, we have two conditions here. C is traversed exactly once as t goes from, let's say, from A to B. Actually, as t increases, okay, as t increases. In other words, for instance, you can have a closed curve, say a circle, right? Or ellipse, or any other closed curve. And you know, if you recall, the same circle, well, we can express the same circle by going once or twice. For instance, if we go twice around, then we're still going to have the same curve. Okay, so if you recall from Calculus 2, a circle can be expressed in different ways. We can express as a circle as cosine t plus sine t, cosine ti plus sine t j, or we can express the same circle as sine t plus cosine t plus sine ti plus cosine t j. The circle we can depends on, as well as cosine 2t I plus cosine 2tj. What will be the difference between the previous two and the last one? Well, the last one we complete one round by going from 0 to pi. We don't have to go from 0 to 2 pi, and so on. So we need to, in order to come up with a function, we need to go traverse it only once. The second condition is that we have continuity. So we're going to require that the vector that describes the curve is continuous. I'm sorry, the derivative vector function is continuous. Okay? Otherwise, we'll have really some weird results. So this is the preliminary to this to the definition of the vector, the arc length function. And what is the expression? Well, the expression will be the following. We're going to say that the function will be s of t, like so. It will be the integral from 0 to t of, remember we said that the arc length is the integral of the magnitude of the derivative vector function. And here I need a variable of integration. Notice that I'm integrating from 0 to t. T is a variable, the parameter. Does it remind you of FTC1? because this is exactly what we are doing. We are using FTC1. So even though we used U already one time, I'll go back and use U and the U. So obviously U is the variable of integration, and we can write it like so if we want to spell it out. Another form for R prime is, or the magnitude of R prime, instead of F, because we have parametric expression, and that's what Kyle showed us. F prime, F is really X equal F of t, G is Y equal G of t, and H is Z equal H of t, and if you take the derivative, then F prime becomes the X dt, G prime becomes the Y dt, and H prime becomes the Z dt. Okay, and we've seen it before. So instead of this expression, we have the square root of the X dt squared plus the Y dt squared. So up to here it's calculus 2, and then we have the Z dt squared, which is the difference between a 3D, a space curve, and a plane curve. And actually it will be du, and du, because the variable t becomes the upper boundary, and the variable of integration is du. Okay? So the x du, the y du, the z du. It's all squared. That's Kyle's bad influence here. Oh, okay. Now, what happened by this is, if you think about it, what happened if you take the derivative? This is FTC1. Okay. Notice that this expression is FTC1. So here's a comment. By FTC1, see calculus 1, if we differentiate both sides, we obtain what happens if we differentiate both sides? We have ds dt equals either this one, but this one becomes dx, the square root of dx dt squared, the y dt squared, the z dt squared, right? Or, in short, we can say it becomes the integrand evaluated at t. So it becomes the magnitude of the derivative vector r evaluated at t, like so. Okay. Or we can write it as the absolute value of dx dt squared, dy dt squared, dz dt squared.